All right, good afternoon, everyone. Question was asked last class, so I'm going to address that question at the top. Question that was asked was about the problem where we are trying to, let's see, 15. Let's bring up the notebook. Here, where we are trying to merge two signals together. And all right, this one. So the question that was asked was, if we have the signal V in of t that is between plus and minus 5 volts, it's a plus minus 5 volt square wave, 10 volts peak to peak square wave, and we are trying to shift it upwards. We are combining it with a DC voltage source of 5 volts. So the question that was asked was, how do we know it's 5 volts? And well, it's from analysis. There's no simple answer or straightforward answer. Like without analysis, there's no way I know. I know that I want to shift it 5 volts up, and so I use a 5 volt source. So what I'm going to do is I'm going to just explain with LT Spice. And then I can also show a manual analysis. Okay. So if you have simulated this, then you already know it. But if you have not, this is the circuit. We have a square wave. V2 is the square wave. V1 is the DC voltage. And let's change that voltage back to 5. And I'm going to run it. Okay. So this V in the waveform in green, that shows you the flat DC voltage at 5 volts. The one in blue, or the dark blue, that is node 003, is the voltage of V1. And sorry, no, that's the voltage for V2. So it goes from -5 to +5, right? -5 to +5. And the voltage across the resistor R1, okay, across the resistor R1, as measured between nodes 1 and 2, is shown right here in red. And the voltage across R2, meaning measured from node 3 to node 2, is shown right here in, let's say, teal, I guess, or blue green. And you can see it's going from -5 to 0. And the one in purple right at the bottom, that's our actual output. And you can see it's shifted from 0 to 5, right? Does everybody see that? Okay. So in green is the DC voltage. In blue is our AC voltage signal. The red shows you the voltage across R1, and the teal waveform shows you the voltage across R2, and the one in purple at the very bottom, that shows your actual output voltage. You can see they're combining, going from 0 to 5 to 0 and 0 to -5, combines to give us 5. So let's use theoretical circuit analysis, and I'll explain how it comes to be. Okay. So this circuit I can draw in this manner. We have our voltage sources. Okay. And V out is here in the middle. Take a few seconds and look over the circuit. It's the exact same thing. It's no different. Okay. This is V1. This is V2. I'm going to call it V1, V2, which is a Vn of t. And this is R2 and R1. Okay. Okay. So R2 and R1, and V out is right here. VO or V out. Excuse me. And then we have our ground reference at the bottom. Okay. Yes. We are not worried. Okay. So question being asked is about R1 and R2. Actually, yeah. Let's get rid of this. Let me just write down 10K and 10K. Sorry. So this is simply the two voltage sources, 10K and 10K. And the red box is basically this. And we are not concerned about that red box just yet. That comes later. Okay, that comes later. So at this point, I'm going to say this is 5 volts and this is 10 volts peak to peak, meaning it's going from -5 to +5. Okay. -5 to +5. Yes. Yes. Yeah. So that comes later. This is, we have a square wave signal and we want to shift it up by 5 volts. Okay. Effectively, we wish to eliminate the negative cycle. It's going from -5 to +5. We only want it to go from 0 to +5. We don't want it to go negative. That's effectively what we are doing, right? We're clamping it up and we're also cutting off the negative half cycle. And so for that, we have a +5 volt source and a 10 kilo ohm resistor. Both resistors are 10 kilo ohm. And then the step after that is that we don't have a 5 volt source. We only have a 9 volt source. So then how do we obtain 5 volts from 9 volts? And that's inside the red box. That's complete. That's the step after that. Okay. So we are not worried about that right now. That's something that's the Thevenin voltage, Thevenin resistance. That's very easy to do. For now, I just want to explain this. Okay. So the way you would analyze this circuit is by just applying Ohm's law, KVL, and KCL. That's all. So let's say V1 is flat, right? V1 is a flat line at 5 volts, right? V1 is a flat line at 5 volts. Okay. And then, and then this disappeared. Then our AC signal is -5 to +5. So for the first positive half cycle, let's stick with green here and show that this is 5 volts, right? That's your DC V1. And then your AC is here. And then AC is okay. So in the first time period, that AC has a level of 5 volts. So if you analyze just for this time period right here, just for this time period, where both voltages are at 5 volts. Okay, if both voltages are at 5 volts, this is at +5, this is also at +5. What is the current that's flowing through those resistors? Zero. You're right, it's zero. If both ends of that circuit have the exact same voltage levels, that means the difference or the voltage between those 2 points is equal to 0, right? If this point is at +5 and this point is also at +5, there is no difference in the level between these 2 points. They're exactly the same. And so the difference between the two is 5. So difference between the two is 0 because both of them are at 5. So if it's 0, there is no current flowing through. Current I is equal to 0. If current I is equal to 0, then the voltage drop across these two is also 0 volts. Now, if you apply KVL, so you have this and you have this. This is your V out. If I say this is loop 1, if I say this is loop 2, I say loop 1 KVL, what do I get? I get minus V1 plus 0 volts plus V out is equal to 0. Therefore, my V out is equal to V1 is equal to 5 volts. If I apply KVL to loop 2, I get minus V out plus 0 plus V2 is equal to 0. So V out is again equal to V2 is equal to 5 volts. That's the mathematical proof of how V out is equal to 5 volts. Okay, so your input is a square wave that's going from -5 to +5. And you're applying a DC voltage of 5 volts to shift that waveform. That waveform is getting shifted. And the reason this happens is because the resistors have the exact same value. So in circuit design, if you're a designer, you're trying to design your circuit and you wish to obtain a different output, then you would analyze the circuit. You would change the value of the resistances, the voltages and currents in the circuit would change, and your output would change. So that's how we kind of know how and why it should be 5 volts. Okay, because we want to shift it up by 5 volts. That's why. So you analyze this and you get V out is equal to 5 volts. KVL is based on laws of physics that are inviolable. Okay, they are a fact. So you KVL apply to left loop, you get the same answer. You apply KVL to the right loop, you still obtain the same answer. Okay. Let's take a pause. Let me know if you have any questions. Yes. That's just the way. So the question being asked is, why is it minus V1? Or is it minus V out? That's just the way I apply KVL. So I would go around the loop. So the question being asked is, why is it minus V out or minus V1? Why is it plus V2 and plus V out, in the two different directions, right? So the way I apply KVL is like this. Let's say I have voltages in a loop. Let's say this is minus, plus, plus, minus, plus, minus. If I apply KVL and I sum up these voltages, let's A, B, C, I know that VA, VB, and VC should sum up to 0. You can sum up the voltages clockwise, you can sum up the voltages counterclockwise, it does not matter. You're just adding up the voltages, but you're going around the loop, right? So you can go in this direction or you can go in this direction where you're adding. So when I start adding, I almost always, actually not almost always, I always choose the bottom left corner of the loop and start going around. If I start going around, when I choose the bottom end of the loop, first sign I encounter is minus, so I put minus. Next I encounter is plus, so I put plus. Third I encounter plus, so I put plus. That's how I obtain my KVL expressions. Doesn't matter. If I was to sum up this way, let's say I started from this loop, from this corner, and I go around this way, what would I get? I would get VC, VB, and VA as equal to 0. In that case, I would have VC as minus, so VC minus, and then VB would also be minus, and then VA would be plus is equal to 0. But they are both the exact same equation. That's how I apply my KVL. The reason I don't emphasize, harp on this is because students have already done KVL, KCL in their prereq physics classes. Some of the students have already done it in your AP physics classes. And so they're already comfortable with applying KVL and KCL. And so I don't like to impose my methods on something that students are already comfortable with. Okay. Yes. Yeah. Yeah. If so, voltage, electrical voltage is defined as the potential difference between 2 points. So the key word is difference. If there is no difference between 2 points, then there is no potential. I mean, there's no voltage. Okay? If electrical potential at both points is exactly the same level, then it's 0 volts. No difference. So that's the simple analysis of how we can do. But let's go to LT Spice, and I want to show you something. Now that you know this, what would you change if you wish to obtain an output that goes from 0 to -5? We wanted to shift our waveform and we wanted to go above, right? So we are going from 0 to 5, but now instead of going from 0 to 5, we want to go from 0 to -5 at the output. What would you change in the circuit? Any thoughts? Hint is the voltage. Yeah, go ahead. No, go ahead. Absolutely. That's the answer. The answer is we flip the voltage source, or instead of applying positive 5 volts, we apply negative 5 volts. Negative 5 volts means we are simply flipping that voltage source. So I'll show it to you here. I can cut it out and do it, or an easier way to do this is simply change that 5 to -5. If I change this 5 to -5, it's now negative voltage being applied, and keep an eye out for the last waveform, the one in purple. Okay, 3, 2, 1, simulate. And look at that. Now it's going from 0 to -5. Okay, so if you wanted to shift it down, we simply applied a negative voltage or flip that source around. So then it shifted it by -5. You can create the circuit in LT Spice. It's very easy to do, obviously. And then you can play around with the resistor values, and you can play around with the value of the voltage source. So if I change this to, instead of -5, let me change it to 10. What do you think is going to happen if I change it to +10? Well, instead of asking you, let me just show it to you. Look at these values. 2.5 to 7.5 volts, going from 0 to +5. It's now 2.5 to 7.5. It's still 5 volts. It's still 5 volt swing, but the entire waveform is shifted up. It's now centered around 5 volts, not 0 volts. Okay, so the waveform, the output is centered at 5 volts, not at 0 volts, or not at 2.5, sorry. If I change it to 20, it should be centered around 10 volts. So let's see. Yep, centered around 10 volts right here. Central line is right there. Okay. When we applied 5 volts, it was centered at 2.5. You apply 10 volts, it's centered at 5 volts. If you apply 20 volts, it's centered at 10 volts. If you apply 100 volts as DC, then that output waveform will be centered at 50 volts. And this is simply a calculation. It's a calculator, so it's simply calculating the voltages that we're feeding it in, right? So it's centered at 50 volts right there because I'm applying 100 volts. But it would behoove you as engineers in training to perform the analysis and see if you can figure, if you can prove mathematically how and why this is correct. Okay. All right, let's take a pause. Let me know if you have any questions. Any questions? Okay. For the lab, do you have to perform LT-SPICE simulations? None whatsoever. So it's only from the class that you have this introduction. So LT-SPICE, if you have not already installed on your laptops or your desktops or your computers, is a very powerful software. It's based on the SPICE software. SPICE is a computer-based calculator for electrical circuits, simulation program. The name of SPICE, the full form of SPICE is Simulation Program with Integrated Circuit Emphasis. It was a project that was developed in the 1960s at UC Berkeley. Okay, it is based on nodal equations. So it's a calculator, and it's a text-based program, meaning you type up your text and everything. And because it was open source, lots of institutions and companies who took that open source code and created their own versions. And LT-SPICE is the version of, it's a graphical version of SPICE based on the original SPICE program. It was created by Linear Technologies, company that is now part of Analog Devices. It's a free software, you can download it, and it's a very powerful tool for circuit analysis. Okay, so you can download it and you can run your own analysis very easily. So this is something that, that is a must for students to learn. Yes. Uh-huh. So the question being asked is, how is it that there's no current flowing in the circuit, right? It's because the value of the battery, the voltage is exactly the same. Then it will start flowing. And it does happen. So the negative half cycle, the square V2 goes to -5. So when it goes to -5, so V2 here is -5. So when it goes to -5, this is what's going to happen. You have +5 at one end, and you have -5 here. So now what is the difference between the 2 points? 10. If it's 10, and then this is 10K, and this is 10K, we can apply voltage division to find the value between the two. But we don't actually have to. What is the value of the voltage between the 2 points? Yep, because it's +5 and -5. Sorry, not 5. Yes, with respect to the bottom node, then it will be 0 volts. Right? Because in the positive half cycle, we already had 5 volts. Negative half cycle, it'll go to 0. But current would be flowing. Voltage would be 0 volts. Yep. So that's how we get the waveform shifted from 5 volts and 0 volts. So this is an interesting little problem. You can, as I said, if you want to do, if you want to broaden your understanding, then have a sheet of paper, simulate this in LT-SPICE, and analyze for both half cycles, as I've just done. And then you have analysis for the first positive half cycle. You also have the analysis for the negative half cycle, right? Here the difference is 10 volts. And so V out would be equal to 0. So it's +5 at one end, -5 at the other end. And you have two resistors which are exactly equal value. Then the midpoint between the two should have 0 volts. But there's current flowing through the circuit. So there's a voltage drop on both resistors, but in the middle, it's 0 volts. In the first positive half cycle, you had +5 volts and +5 volts at both ends. In the middle, you had +5 volts. And so it keeps changing. Okay. All right. So let's see. Continuing with this. And then after that was the portion in, not the portion, but the step about finding this, because we only had a 9-volt source. So how do we obtain a 10 kilo ohm resistance and a 5-volt output or 5-volt source if we only have a 9-volt battery? Right? If you only have a 9-volt source and you wish to obtain 5 volts from it, how do you accomplish that? What do you need to do so? And that's where that red box comes in. Okay. And that was the portion about the Thevenin voltage and the Thevenin resistance. Okay. That was all of this analysis right there. All right. Come on. It's getting stuck. Okay, so here we were talking about conductances, right? We're talking about conductances and current division. And so the summary of both is on this slide, this page. If you have parallel resistors, voltage is the same, current is divided. By its very definition, parallel means they are connected to the exact same two nodes. So if it's the same two nodes, then the voltage is the same for anything that's connected between those nodes. And the division of the current, meaning, let's say you have R1, R2, R3, and Rn. And you wish to find currents I1, I2, I3, all the way up to In. Then by applying current division, you can simply do G1 or G1 plus G2 plus all the way up to Gn. And so for parallel resistors, it is easier to use, or far easier and simpler to use, conductances rather than using resistances. Okay. And then voltage division applies to series resistors. Where if it's a series connection, of course, the current is the same, but voltage is divided. So again, if you have n number of resistors in series, and you're trying to find V1, V2, V3, all the way up to Vn, then it's simply, oh, this is times your source current Is, and this would be simply R1 over R1 plus R2 plus all the way N times your source voltage Vs. Okay. This remains true no matter how many components you have connected in that parallel or that series circuit. N number of resistors in parallel or n number of resistors in series, you can very easily apply voltage division and current division. This is something I may ask on the quiz on Monday. Voltage and current division. Okay. The understanding that equation is the most important. After that, it's simply plug and solve. Any questions? Mm-hmm. So the question being asked is, if we have a resistive network that has a combination of series and parallel resistances, and then we try to reduce them, so we can, yes, we can apply voltage and current division, but only to that specific portion of that network. Meaning if let's say if there is a circuit comprised of 100 resistors, and out of 100 resistors in a small part of the circuit, there are 5 resistors that are in parallel. Then we can only apply current division to those 5 resistors based on the current that's coming into those resistors. That, in fact, is the purpose of using current and voltage division. No, that's fine. That was in parallel with some in series. Okay. Yes, that is correct. Yes. So the question being asked is, if we have, let's say, 5 resistors in parallel and there was a 6th branch that was in parallel, that 6th branch had multiple resistors in series. So then, yes, we could combine all of them, reduce it to like one single resistance. And so that 6th resistor would be in parallel to the rest of the 5. Yeah. Okay. So this was assigned as home activity. How many of you took a crack at it? No one? Got it correct? Any questions about this activity? No questions? For those of you who did attempt this, did it make sense? Just one student. Yep. 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 So I think the homework question had like what, three sources. Yeah. This one's unique. Well, not unique, but it made it convenient because you have 5 ohms here, you got like 5 ohms here also. So it's very straightforward to solve. Not that difficult. And then let's see, I think it was just LT Spice simulation, the last one. So the solution is given right here. Okay, you can do so. And then there's some additional questions on the slide after this one that I'd like students to think about. You don't have to worry about this, but I could possibly encounter something similar on the quiz. Okay. All right. Yeah. So question being asked is the quiz questions, would they be conceptual or would they be part of the problem? Uh, is that the question? Yeah, I haven't yet decided. It could be a straightforward problem where it'd be like a simple portion and then it will test both the concept by asking students to calculate the values. So let's put it that way. Yeah. We saw an example of this just a few minutes ago when we did the LT Spice. We saw how we can flip the voltage source and we can see what happened, right? And so that's something to think of. Yes. So what would happen if I flip the current source? What do you think is going to happen? Which one? Would the current become negative? I don't know. One way to think about this is, let's look at the voltage source, right? The voltage source, is the current flowing up or is it going down? It's going up, absolutely. So if you flip the direction of the current source, it's now pointing up. So if both currents are coming up and they're meeting up at the node, how do you think it affects the other current that's leaving the node? It'll increase. Because instead of being in opposition, it's now summing up. So if you flip it, you're saying this, right? This question. Oh, sorry, not that. You're talking about this one, right? Flipping it up. So it's now pointing up. So you have two currents coming in. You have this going up. This is also going up. And they're meeting at this node. If they're both meeting up at this node and you apply KCL at that top node right here, third current is going here. That must increase. That's the answer to that question. Everything is based on KVL, KCL, and Ohm's law. In case you have gotten tired of hearing that. It's based on KVL, KCL, and Ohm's law. All of circuit analysis based on these three laws. That's it. All right, let's introduce other applications. So there are some signal processing applications of resistors to our ladder networks. That's part of the signal processing. And then there's also one of the most important, which is biasing. Okay, Bias, B-I-A-S, bias is an important function in circuits. Bias simply means you are constraining your circuit or your system, electrical system, to function within a certain range. Okay, so you're forcing that circuit to only work with a certain range, and that's what it means by biasing the system. You're setting up the functioning of your circuit. So when we say bias, simply put, we are applying a certain amount of voltage or we are applying a certain amount of current. So we'd say we are applying a voltage bias or we are applying a current bias. That's all it means. So in simple terms, biasing simply means the application of voltage or the application of a current to ensure that a circuit is working within a specified range. Okay. As a real life example, and this is directly related to this slide. You ever use a clothes iron? Right? If you use a clothes iron or if you have a electric cook stove, you have an electric cook stove with a dial that goes from like off all the way to like high, right? In both cases, what you have is you have an electrical, you have a coil. When you turn it on, current's passing through the coil. That coil is conductive, but it also has resistance. It's going to oppose the transfer of this electrical current. The byproduct of electricity passing through this resistance is that a lot of the energy is dissipated as heat. Electrical energy is converted into thermal energy. In electric and electronic circuits, the heat is completely undesirable. We don't want it. Electrical circuits, we don't want heat. Okay, absolutely undesirable. We have our devices getting hot, tablets get hot, cell phones get hot, laptops used to get, laptops still get hot, desktops get hot, everything gets hot because it's a byproduct. A lot of the electrical energy is lost as heat. However, it is desirable when you have a hair dryer, air fryer, cook stove, clothes iron, electric heaters. All of these places, we intentionally generate heat. So that's where it's desirable. So in those applications, you have electric current flowing through a coil or a kind of like a resistive material. The byproduct of that is heat. We can use that heat, iron our clothes. We can use it to cook. We can use it in air fryers. We can use it in space heaters, like electric space heaters. So that's where it's very desirable. Now, if you turn the dial, whether it's on a cooking range or whether it's on an air fryer or on a clothes iron, you're turning that dial. That dial is changing how much voltage or how much current is actually going in there. So we are changing the bias of that device. By changing the bias of the device, we are forcing that device to operate at a certain level. If we want to cook at 200 degrees Fahrenheit in our air fryer, we're going to turn the dial, set it to 200. What it's doing inside the device, it is forcing a certain amount of voltage and current to go into our device, not more than that. So we are forcing it to operate within the certain levels so that it does not go beyond 200 degrees Fahrenheit. And that's called biasing of the system. Does that make sense to everyone? Okay. So again, in general, in electric circuits, heat is undesirable, but it's a byproduct of electrical conversion. Conversion of electrical energy. So it converts a significant chunk is converted into thermal energy and is dissipated as heat. This is also the operating principle of an incandescent light bulb. Okay, we have a tungsten filament inside a vacuum sealed enclosure. You pass electric current through it, it gets hot, and because of the design, it also emits light. Okay, so electrical light bulbs or incandescent light bulb is simply based on the same principle. It opposes the flow of current, but the way it was designed and created was that a lot of the electrical energy is converted into thermal energy as well as optical energy. Of course, filament light bulbs are no longer used in most parts of the world anymore. Everywhere, LED light bulbs have become the de facto standard. And LED is a light emitting diode, which again, based on electrical principles, is taking electrical energy, and the emission that occurs, there's a little bit of thermal energy that is dissipated, but most of the energy is converted into optical or light energy. And so those diodes emit light. That's a byproduct, but we made it into a main product. But there's, again, heat is a byproduct even in LEDs. So you can have a LED light bulb, and these are LED lights right here at the top. They still have thermal energy dissipated, so they do get hot. Okay, if you ever change out the light bulb, an incandescent light bulb gets really hot because a lot of the electrical energy was dissipated as heat. In a light bulb, most of it is dissipated as light, but a still significant amount is dissipated as heat. So even LED light bulbs will get hot. You try to use a LED light or handle a LED light bulb after it's been in operation for like 30 minutes or an hour, and you will feel that it's warm. Okay, so it's not as if they don't get hot. So anyway, the takeaway is anytime you have conversion from one form to another, energy is converted from one form to another, there's always losses that occur. And most of the losses from conversion of electrical energy into useful forms is as thermal energy, which is heat. That's just an unfortunate byproduct. Okay. All right. So well, actually, I still have 2 minutes. I'm just going to summarize on what we are going to do. So there are these applications. What we are going to look at is a little bit of biasing. We're going to look at diode circuits, resistors. We already saw this, right? Resistive circuit dividers or voltage dividers. And then let's see. Come on. I don't know why this keeps doing that. Here again is a voltage divider network. I will go over this on Monday. And then op amps and comparators. So the next few weeks, we are going to deal, or we're going to learn about circuits involving diodes and op amps and comparator circuits. That is what we're going to study. Okay, that's what's coming up next in the next few weeks. And in the final week, we'll look at two analysis techniques, which are used for solving circuits. One is nodal analysis. The other one is mesh current analysis. But that's at the very end. Okay, but for the next few weeks, we'll just look at diodes, resistors, applications of resistors, and digital and analog comparators. Okay. All right. So we'll end class here today. We'll see you all on Monday, based on the material we have covered this week. And I've pointed out a few things. So homework 2, superposition, voltage division, current division. Okay, those are the topics that will be assessed on the quiz on Monday. All right, have a good weekend, and I will see you all on Monday.